Hello, thank you for attending my talk titled Connecting the Popularity Adjusted Block Model to the Generalized Random Dot Product Graph. This is joint work with Min Tang, Assistant Professor at NC State University, and Michael Trossett, Professor at IU, where I am currently a PhD student. So very briefly, here's an outline of my talk. Before we dive into our contributions, we first need to define the popularity adjusted block model, as well as the generalized random dot product graph. Next, we will show how the PABM is a very special case of the GRDPG. And then finally, we will discuss two community detection methods for the PABM based on this connection. So let's begin. First, I want to introduce the block model. Suppose we observe a network with binary and undirected edges, for example, a Facebook network, in which the nodes are individuals and edges represent whether pairs of individuals are friends. One analysis technique might be to partition this network into groups in an unsupervised yet meaningful manner called graph partitioning or graph clustering. There are, of course, infinitely many approaches to this task, but we will take a statistical inference-based approach by defining a probability model and trying to estimate the parameters of that model, namely hidden and unobserved labels associated with each node. Let's describe this network by adjacency matrix A, such that A sub ij is 1 if there's an edge between nodes I and j and 0 otherwise. We say that this graph is a Bernoulli graph if it is sampled from some other matrix P, such that each A sub ij is drawn independently as Bernoulli P sub ij. In addition, if the nodes have hidden community labels 1, 2, up to k, and each P sub ij depends in some way on the hidden labels zi and zj, then this model is called a block model. For instance, this two-community stochastic block model defines P such that P sub ij is 1/2 if I and j are both in community 1, 1/4 if they are both in community 2, and 1/8 if they are in different communities. Another more flexible block model is the popularity adjusted block model. To define this, first let's organize P by community such that the k-elf block of P represents edge probabilities between communities k and l. Then, for each pair of communities, there are popularity vectors lambda kl in n sub k dimensional space and lambda lk in n sub l dimensional space, such that the k-elf block of P is the outer product of lambda kl and lambda lk. Now that we have these block models, we want to go back to our original problem of graph partitioning via community detection. Unfortunately, likelihood maximization for these problems is NP-complete, so we need to take a different approach. In order to motivate this, we will introduce another type of Bernoulli graph called the generalized random dot product graph. In this model, we start with latent vectors x1, x2 up to xn in Euclidean space, and we set the edge probability between each pair I and j by taking the indefinite inner product between latent vectors xi and xj. Under this model, an inference task might be to estimate the latent positions after observing one draw of the model. The adjacency spectral embedding does this by taking the spectral decomposition of A, and it has already been shown that the ASE asymptotically approaches the true latent positions up to an indefinite orthogonal transformation. Now, it's easy to show that all Bernoulli graphs, including all block models, can be represented as generalized random dot product graphs, simply by taking the spectral decomposition of P. It's well known that the latent configuration that induces the stochastic block model under the GRDPG framework is a collection of point masses where each point mass corresponds to a community. Our contribution shows similarly that the latent configuration that induces the PABM consists of orthogonal subspaces, where each subspace corresponds to a community. To illustrate this connection between the PABM and the GRDPG, we will take a look at the case where we have two communities. You can decompose P for the PABM in this manner, and we can see that the latent configuration is four-dimensional and consists of a block diagonal matrix times an orthogonal matrix, where each block is rank 2 and corresponds to a community. Thus, the latent configuration for the PABM consists of two-dimensional subspaces that are orthogonal to each other in four-dimensional space. This easily generalizes to k greater than 2 in the same manner. Our theorem states that if we have a PABM, we can compute an x that is block diagonal and u that is orthogonal such that the model is GRDPG with latent configuration xu. Furthermore, the latent configuration is such that if two vectors xi and xj belong to two different communities, their dot product is 0. We call this the canonical latent configuration for the popularity adjusted block model under the generalized random dot product framework. One thing to note is that the latent configuration is not unique. For each P, there are infinitely many latent configurations that can be used to construct P under the GRDPG framework, and these are all tied to the indefinite orthogonal transformation. So while our canonical latent configuration for the PABM is not the only latent configuration, all latent configurations that induce the PABM consist of subspaces with one community per subspace. Furthermore, we were able to construct a type of adjacency spectral embedding that enforces orthogonality between subspaces, the details of which we omit in this presentation. So, how does this lead to community detection? Since the latent configuration for the PABM under the GRDPG framework consists of subspaces, the ASC consists of points lying near subspaces with some small noise that goes to 0 with probability 1 as n increases. There already is a family of algorithms for this type of data called subspace clustering, and we will focus on sparse subspace clustering, which constructs a graph by solving n optimization problems. A collection of vectors X obeys the subspace detection property if sparse subspace clustering results in a graph such that vectors Xi and Xj belonging to different subspaces results in there being no edge connecting the two. While they did not make the connection to the GRDPG and did not apply any embedding techniques, Norozi, Rimal, and Pensky noticed something very similar and proposed using sparse subspace clustering for community detection on the PABM. Our work extends what they did by showing that the SSE algorithm using the ASC of A as the input obeys the subspace detection property with probability 1. Next, we examined the eigenvectors of P for the PABM and saw that if we select two rows that correspond to different communities, their inner product will always be 0. This led to our own community detection algorithm called orthogonal spectral clustering. Here we show that if V are the eigenvectors of A, then as n increases, the inner products of the rows of V that correspond to different communities goes to 0 with probability 1. Now here is a simulation study of the various community detection algorithms for the PABM. In each simulation, community labels were sampled from a categorical distribution, and the popularity parameters were sampled from a beta distribution to construct P. Then A was sampled from P. And finally, we applied these 4 community detection algorithms for each A. Here, the red curve is modularity maximization using the Louvain algorithm, which circumvents embedding and dimensionality altogether. Blue is our orthogonal spectral clustering algorithm. Green is sparse subspace clustering as implemented by Norozi et al. And purple is our version of sparse subspace clustering on the adjacency spectral embedding. In these results, we can see that for k equals 2, orthogonal spectral clustering outperforms all of the other algorithms for large n, and for k greater than 2, orthogonal spectral clustering and sparse subspace clustering have similar performance. Our theorem states that if n is large enough, orthogonal spectral clustering will result in perfect community detection, and the adjacency spectral embedding will obey the subspace detection property. So in conclusion, we explored the popularity adjusted block model, which is a flexible block model that can describe many graphs with community structure. However, standard statistical inference techniques, such as likelihood maximization, is difficult for the popularity adjusted block model. Instead, we motivated a spectral method via the generalized random dot product graph, which can describe all block models, including the PABM. Under the generalized random dot product graph framework, the popularity adjusted block model is induced by latent configurations in k-squared dimensional space, and consists of k-dimensional subspaces that are all orthogonal to each other. The latent configuration of the popularity adjusted block model under the generalized random dot product graph framework leads to 2 community detection methods, the first of which is a pre-existing algorithm, sparse subspace clustering, and the second is a new method we call orthogonal spectral clustering, both of which have nice theoretical asymptotic properties. Thank you for attending my talk. You can see the code and paper for this work on my GitHub page, and I hope to have an R package for the 2 algorithms described in this talk on there as well.